The first speaker today is Sophie Pennetier. I think she's well known from the audience. She will be introducing scaling reglass, so she asked me to not introduce her, she will introduce herself. So welcome, Sophie.
Thank you so much. Yeah, I need that extra time. Good morning, everybody. Can I get a sound up a little bit, please? Thank you. This morning I will be presenting the scaling of our prior glass recycling research, and a few words about myself. I'm a structural engineer, and I've experience in both consulting and contracting. I was more recently with Enclosures, but I left a year ago to spin off my own startup called Digne. Baijin, who's with us today, is also part of Digne. And this is Baijin, in case she was not going to be in a room today. And this is us, this is Digne. So we are a collaborative of architects and engineers looking to advance circularity and low carbon technology, mainly where we are in Los Angeles. So again, that's a spin-off of being a contractor for the last 7 years. So we have a strong focus on EPD, environmental product declaration, life cycle assessments, and so forth. Meanwhile, I teach at the School of Architecture in Los Angeles called SCI-Arc, Southern California Institute of Architecture, teach facade structures and the like. So Digne, as I was just saying, provides environmental product declaration and life cycle assessment services to building materials manufacturers. This is the bulk of our cash flow, actually. And I'm a proud advisor to the construction company, non-profit, the Reuse People. We are a labor incubator, so we give the opportunity for recent graduates to muscle up their knowledge and skill sets in the carbon and decarbonation space. And we also do materials R&D, so this is what we'll be talking about today. And we are located in Los Angeles, so we're daily reminded of the climate question. This is how I trigger my students' first day of school in carbon class, you know, like, don't forget, never forget. So spinning off on the works that I've presented at multiple conferences before on the circularity work that we did with Enclosures when I was steering our sustainability efforts. We keep a strong focus on labor and value proposition. So lots of folks are telling me, why do you use this crap glass that's so contaminated? Well, there's definitely a case on the value proposition today. According to the National Glass Association, most of the glass, architectural glass in the US, goes straight to landfill. It's because it's the cheapest thing to do. We have no money for anything else. We gotta work with that contaminated glass. And so as we're gonna make our way through, you know, no longer landfill and going into a circle that's becoming a real circle, we gotta start where we can, where the value proposition is gonna be A+ amongst all this Fs of, yeah, probably not the most circular, but this is what we can do. So our students are designing with waste. One of them, again, being Baijin, has been looking at disassembling IGUs that have been, there's like 1 foot samples donated by SOM, Los Angeles, in developing the art of accommodating leftovers. What can we do with what we have? So she's been developing those tiles that are basically consisting in fusing in electric kilns cullets that are coming off of those glass at end of life. In prior works that you can see, it's published on our website, you can download the paper. We've structurally tested those samples, and in a nutshell, the outcome was the structural performance of those tiles was lesser than of annealed glass. It performs pretty much like a stone. As for the color, we've observed and also published that when you melt low-E coating may look tinted, a little gray, a little blue in your fresh glass. When you melt it, it becomes yellow. And we did some research, more grassroots, and then more lab. The research being, like, what's the leftover. You know, we were looking at what's the leftover structural performance, what's the leftover emissivity performance. So we looked at whether in the infrared and ultraviolet spectrum, we would get any preservation of the low E performance? The answer is no. We did not preserve any low E performance. So this is mainly just colors that's left over as the silver and low emissivity materials just melted into the glass, into the body of the glass. You literally have the low emissivity performance as just tinted glass. But we don't lose sight of why we do that. So yes, not low emissivity, but we operate at a low carbon space. So on the left of the graph here, this is cool, this is like weather forecast. On the left of the graph, you have here the EPD, Environmental Product Declaration and Global Warming Potential of Regular Flat Glass by the National Glass Association. Typical commercial producer will be a little lower than those averages. And as we go into the space we operated at a minus 70% or so carbon footprint. So we are, a third also of the carbon footprint of a fresh sheet of glass. And as we operate with electricity, and in California, we're hockey stick, like really rapid growth in the solar and other renewable energy grid, we're likely to near net zero, not net zero, but very, very low carbon solutions very soon for our electric production. So since the last couple conferences, we've been developing those products with the team, spanning from, on the left, the tiles that Bejin has been working on, into other exploration over the summer. We'll talk about it in a second, all the way into well, we'll talk about it in a second, but Circularity Awards. So why we did that, we are working on a project in Little Rock, Arkansas, which is a new neighborhood development actually for housing homeless folks from Little Rock. And we've been invited to develop products that echo the circularity of I don't need to go into much details, but like having recycling glass into this vision of this neighborhood. This is Acacia Lee here, exploring the arrangement of cullets to develop her murals and installation all throughout the buildings as we are scaling, again, those efforts. So this is one of the murals that she's been developing. And as we were doing so, we were developing those products at Judson Studio in Los Angeles. You see here in the center, second to left, Quentin with Judson Studio. Judson Studio is a 125-year-old glass shop in Los Angeles, and they've been supporting our efforts from day one. So Lisa was around and saw what we were doing, and kindly invited us to cut down some of our work and slates into the awards that were ultimately distributed to leaders in this field at the other glass conference, Glass Tech, the Circularity Awards, honoring the leaders of our field of circularity. So we don't get awards yet, but we make them. We were also invited to present our efforts as well and showcase the work of Bejin. But we stay focused. In January, we were stuck home, 14,000 structure burnt in Los Angeles. So we stay focused. There's a climate thing to resolve. And a little side note, with SciArc, we've been scanning and surveying sites to support Altadena mostly, where two of my colleagues actually lost their homes. And we found in the rubbles the color change that we had been working with. And so, daily reminder about what we do and why we do it. So if you want, we have a lot of content on Vimeo, actually, to look into all those events, half a dozen events so far, where we've been supporting the homeowners of Altadena, and specifically for glass, you'll find a few hints that should be in a report pretty soon. But back at it, we've been seeing a lot of increase in the number of students that want to do something and use their creativity for, low carbon and climate conscious solutions. And so we've had two new members, Jamie and Min, join the team and helping us with developing those products. So explorations here, and then here the largest plates that I will be talking about in a second. So students, again, are put to work. This is fantastic. Helpers looking into disassembly IGUs and the contamination also due to primary and secondary seal and how to address it. And then we are not Darmstadt, but we have done structural loads in the shop, basically piling up loads onto our plate in an extremely scientific way, but we had a witness, so we're good. And this is the plate on the right after breakage. And notably, we had, well, I'll talk about it in a second. This is the class, this is the group. This is by Jean Elisa. So the plate itself is for the project, the Arkansas project I mentioned. And the order of magnitude of it is not for it, but this is one research step towards that project for that nonprofit that I just mentioned in Arkansas. The plate itself is about 900 mil by 400, with thickness varying from 8 millimeters to 15 millimeters. And here you can see the size of the cullet, so about 4-6 inches varying. The yellow color, again, is the leftover low-E coating, and the dark elements right there is basically tinted glass that we had as part of our samples. This is glasses for scale, very scientific. So things to mention, there's a lot of rugosity of the surface, so lots of inconsistencies in the thickness of it, very obvious. Also on the edge, some pinch points, which we will avoid for next steps. And this is where the glass would have broken, not specifically this area, but something quite similar. But also some interesting way to show you the material as you see through. Blue sky or white ground. And within the body of the panel, we had much better homogeneity. So as we advance these products, we have better methods to remain low carbon for the energy we use, yet having better melting and homogeneity within the body of the glass. This is why we were able to achieve much better structural performance than we had in the prior state. And things to be mentioned, we also had much better translucency, limiting vitrification that we had in the former samples. And we're able to tune a few phenomena, such as when you flip your air and your tin side, you start to have some really interesting translucency as opposed to transparency. So there's a lot of parameters that we developed. All again, this is air side, tin side flips, so you can really start to play with those. So for the structural loads, we had breakage at 140 pounds. That's about 60 kilograms, 64 kilograms. And we had, I believe, we did have, not believing, a very reduction in thickness locally. Whereas our plate was 40 millimeters, we had 8 millimeters there. And so a little bit of concentration amongst our spreading plates, which were aluminum plates within the softness of a cardboard, for no direct metal to glass contact. However, we had a little bit of concentrated loads. So the numbers we will get are extremely approximate due to the concentration that is there. So we had a first breakage there, followed by, when everything fell to the table, we had the second hinge right there. So these are extremely preliminary results, call them napkin. As we are going to actually, we have started to model our plates with methods of scans and also visual tracing. So we'll get better results pretty soon. But where we are right now, if you are to look at the clear span, we had about 800 millimeters of clear span, 63 kilogram approximately, and so the stresses were in a ballpark of 30 MPa. We expect this is actually much greater stress because these are just getting calculated with a very basically simple span calculation. So we definitely should have localized much higher capacity. Next steps are going to be exploring those areas of breakage and the initial crack, so that we could have better understanding of the stresses. But we're going to also do this in parallel to product development, so we won't spend a ton of time on getting in the weeds of this specific samples, because we are changing already a few parameters. Very lean approach to, a very agile approach to product development. But we leave it at this. The idea is, again, to show that trash can be beautiful ways to a way to produce new materials. You see here the low emissivity cracking right there, that you can control a little bit, as well as I was telling you earlier, the flipping of the air side and tin side for the samples. So in closing, there's a lot of work to be done. We can't wait to show it to the next conference, and we'd like to acknowledge and thank Judson Studio for letting us using their kilns pretty graciously, as well as SciArc, Lisa and Linda for allowing us to support our efforts by bringing our awards to their conference. USGBC California is supporting the spin-off of Digne, the Reuse People and SOM for providing us some materials, and of course the full project team. You can find a QR code here to our website, and we may have some time for questions. Thank you so much.
Thank you very much, Sophie.